Greetings, healthcare colleague. My name is Kawchak. I'm the founder CEO of Chemical Q Device, here today to go over some demos. So this first demo is basically inserting the brain data set that I've been looking for, and it's local on the computer. So I'm running the code right now. It just takes a little bit, and it'll eventually display as it goes through these stars the an example of an image. Oh, here we go. Okay. So in this specific one, so this is a database of over 5,000 images, and what it's leading up to is a classical convolutional neural net. But I took a couple of tutorials on it. So it's just showing, for instance, this single image now, because the code's saying to basically break at this point. If I take that out, it'll start to go through all of these brain images. Now, keep in mind, you see this is the back of the head. So that you get a whole, in these data sets, whether it's cats and dogs or MRIs, you get a whole slew of different images. This is a Kaggle database with 4 different types of brain classified images. I'll show you from above. So in that case, I don't want to load over 5,000. I'm gonna go ahead and stop it. And then, like I did before, to do that, I'm going to run it again. And then again, I'll see the single image. So the ones in specific for this brain tumor set is glioma, meningioma, no tumor, and pituitary. Okay. So then it prints out this array. So 0 is black. So you can see on the corners, they're all black. And I believe that's why that's 0. And then I'm going to go through this tells you the type of data it is. So it's a uint8. And then this specific one is the shape. So it's 512 pixels by 512 pixels, which is a nice size for medical images. And then here, this reduces down to 256. So this specific image that it's looking at is going to start to look less sharp. So the 256 by 256. And again, when you have AI, and basically getting less scans in an MRI, there's specific ways around having to have the best images with AI. So this is a 128 by 128. Here's a 64 by 64. And you can see here, it starts to get pixelated. But again, it may be workable images. It just depends on the rest of the data set, a number of different factors involved. Here's 32 by 32. Here's a 16. And then here's an 8 by 8, and you can actually count the pixels across. So 1, 2, 3, 4, 5, 6, 7, 8, and then it goes 8 in the other direction, and that's that image. That's what that looks like. So this particular one, like I said, it's a Python tutorial. The author, his name is Sentdex, Sentdex, and he has a number of good tutorials. So he was doing cats and dogs. I'm doing these brain images. And it may be an issue, I'll show you a little bit further down. So it's basically when you do machine learning, or this is a convolutional neural net, you have to create these objects and training data. So basically, it says at this point it's still good. It's saying there's 5,712 images, and that's how much is local on my computer. And then it's going to shuffle the data. This is a test to make sure everything is okay. And I'm assuming that you don't get something random like that if it's not. But then you have, setting up, this is capital X, lowercase y. I've had to fix that. And the pickle is a big point. So, it's basically, you could save and do things later, but you'll see this in my data set, x.pickle, y.pickle there. And, so that cell ran 61, and then see how I put to open later. And then this is part 3 of it. So this is where I had, keep trying to, address this issue. But basically when I run 64, and you'll see these types of things, pooling layers, convolutional, dense, binary cross entropy kind of stuff. So in those specific cases that, they're very standard things. So I'm getting an error, and then that's what I'm addressing right now. So I'm going to switch off this, and I'm going to switch into, let's see, some Qiskit. And let's see here. I close that. And the Qiskit is it's just very easy. So I'm going to log into Qiskit, and then I'm going to go into composer mode. So in this specific demo, I'm going to open this. It's a paper by Roche and QC Wares. If you're not familiar in the quantum realm, they're very prominent. So the best way to do this, let's see here, this, and then that, and this. So here is this specific one. And if you haven't got going, basically with this, I'm going to be doing a 5-qubit circuit. So the easiest, I'm more getting used to the code as opposed to just dragging and dropping with these things. And I'll show you a little bit with the code basically. So Qreg is the number of quantum bits. So that's going to be 5. And this typically matches to 5. So we have Q0 through Q4. Now this specific circuit I chose is basically because it was flipped in the paper, so I had to put it into my Google Sheets and then do a flip so that I could see what the Q0 is, how I'd be entering it. So it was interesting doing it like that. But basically H, and then you have a space, and then with this thing. So you have Q0. So they want Hadamard gate on Q0. You have that. And the codes between, this is matplotlib, which is different color scheme than this particular setup. They want 4 Hadamard gates to begin with. So a lot of times this copy and paste is just easier. And then I can just change 1, and then 2, and then 3. And then they want an X gate. So for all the single qubit gates, it's relatively easy. So this X gate at qubit 4. And then it's the language of semicolons. I don't know if anybody else has ever said that, but that's how it seems. So I'm going to put a space in between each of the layers. So I've got another H, which is Hadamard. That's at Q, let's see, Q4. And then here's your semicolon. And then done with that later. Now the next one is a CZ. This is going to be at a Q2 through Q4. And as with many other languages, you'll see commas separated. It's just easy to get to on the keyboard here. And then there's a semicolon. Okay, so I got a CZ in there. Now I'm going to do some RYs in the next one. So RY. And if you forget how to do this, basically, if you do RY and then just tab, it'll tell you what it wants. So theta is the angle. So I'm going to go negative, and I got to type in pi divided by 4. And then A is kind of tricky, but it actually stands for the qubit, which is at Q, and then this is 2. Okay. And then, so the next one is basically another RY, but it's positive, and it's at Q4. So if you're not doing it by code and drag and drop, and the more complicated ones, it just gets kind of interesting. So next layer. So this is actually similar to this. So it's the same exact thing. So a CZ gate to put in there. And then I'm going to do a space. And then I'm going to have another CZ, but it's 1 and 2. But here's my 1. There's my 2. And then another space. And then these are a bunch of RYs. So again, it's perfectly fine to copy the code that you just made. And then this is, they put in a value. Now this is an optimized circuit. So they want negative 1.19 for that. And then the next line, they want a positive. And then it's at Q, these are at Q1 and Q2. So just like that. So then the next is it wants more CZs, space, CZ. And then the next, it's more space. And we have CZs at 0, 1, 0, 1. Okay. And then we have a space at, or actually no space, but this is 2 and 3. So here's 2, and then here's 3. Okay. So you'll see those like that. And after we finish here, so after those are in, these are 4 RYs. So the first one's going to be negative. I'll just take this. So my RY is negative, and this is negative 3.25. And this is going to be at Q0. And then I've got a Q1 RY, and then a Q2 and a Q3. So with this one, negative 3.25 at Q0, and then we have a positive 3.25 at Q1, and then the next is a 0.34. And you start to see some patterns here with the, the plus minuses, basically. Again, this is an optimized circuit, meaning that there was additional effort to make this better. So, and then you see the 0.34, and then here's a 0.34. And this is going to be a Q3. Okay. So we're going to do a couple spaces. Now there's a repeat here. So we have a CZ again at that. So there's 2 CZs. And then this next one is an H at Q, and that's going to be 0, semicolon. And then there's going to be a CZ at 1 to 2. So Q, and this is 1. And this is 2, and then semicolon. And then we're going to have another H, but this one's going to be at Q3. H at Q3. Okay, so coming towards the end of this, there's a repeat here in some RYs. So I'm going to copy, paste. So this first RY is a 0.633. So 0.633. And it's going to be at Q1. And then the second one is an RY at Q2. And it's going to be a negative 0.633. Okay, and then we've got another kind of repeat here. So this is another CZ, and it's going to be here. So between 1 and 2, and then next level is H, and this is going to be at Q1, and this is going to be semicolon. And then there's another CZ, and it's going to be between 2 and 4 here. And you don't necessarily have to put in these spaces. I just do it for if there's trouble shooting later, 2 and 4. So you can see the circuit's looking pretty good right there. And there's just a couple more lines here. So this is going to be an RY. So we're going to RY, and then it's pi over 4. So you can't, there's no thing for the pi, you have to type in pi. So I think it's its own thing. It's gets special treatment too. And then it's Q2, and then we have another one. Oops. Copy, and then another one at negative pi over 4. And then there's another C. Actually, I can do this. The last CZ is the same. Oops. Copy, and then here, and then we got some H's. H at Q2. And again, I'm going off of it's like a transposed image off my phone, because when they publish in the paper, they flip the gates. Now the Q, say for instance, Q0 will have this first Hadamard gate. And, it's flipped over the y-axis. So I had to do that on my own. And then my last gate is going to be at 4, and then semicolon there. So basically, you can scroll back and forth, or you should be able to. So, okay, so HH, this, and then there's a mistake. So this is RY. The last RYs should be 2 and 4. And that is positive, negative. And then HCZs, RYs, H. And let's see here. Okay, so RYs H, and then these two RYs are 0.6 and negative H, CZH, CZs, negative, positive, positive, negative, and then some CZs, and then negative, positive, negative pi plus boom, boom, H. Now, if you've had experience doing circuits, there's one thing missing. And by the way, actually, there's a couple things missing in order for me to run, is I do need to put in these specific resets. So, and I need to do measurements. So on papers, they don't always include these. So there's 5 qubits, so it's going to be 0, 1. There's going to be 2, and then there's going to be 3, and there's going to be 4. So remember, qubits 0 through 4. So on the circuit here, it doesn't show that, but I actually want to run. So I always do a break. So this is a barrier. So, and if you just type B and then tab, it'll put it in for you. And then I click anywhere else. Doing enter at that stage doesn't do too much. So this barrier is inserted to put in measurements. So I'm going to put measure, and it tells me how to do it. And again, don't forget the brackets, but it's always Q, and it's going to be bracket Q0, and then it's going to be C, and then bracket 0. So you see the first measurement is in the more complex circuits, or this isn't too complex, but it keeps the measurements from sliding around. So here's my second one, and Q1 to C1. Here's my third, which is Q2 to C2. And then here's my fourth, it's Q3 to C3. And then here's the fifth, which is Q4 to C4. And then at this step, you just want to take a look at your circuit and make sure everything's right. Like I said, I'm going off of this transpose circuit from my phone. And you'll see all the gates, these 2 qubit gates, single qubit gates with all of this. And it's looking pretty good. I named this demo. And again, this is so when I hit enter, I can see it again. But Landeman et al., this is the Roche and QCware. This is a big medical imaging paper with quantum. This specific circuit is a 4,42 qubit assisted, meaning that it runs with a classical convolutional neural net. So I always make sure to hit enter, before it does that. Now the save part, it just means it saves the circuit. It doesn't mean it saved your title. So you always want to make sure to do that before you go run. I'm going to go to setup, and then on this specific part, so I just hit run my 7 qubit real quantum computer. And then at this stage is pretty easy. And I want to show you, and I'll see, this is the first time I ran and conducted this specific circuit, but I'm going to copy this code. And then I'm going to go over, and this is where we're going to wind up, is in lab, the specific one here. Now, sometimes it says that the server's not, you just need to restart the server right there. And this just takes a second. Okay, so this is what it looks like, and it saved the last place I was at. Now there's this code that's chasm to MPL, and it's basically at this point you insert your code here. So I'm going to insert the code here. Now in this specific code, it's important to keep these. It's a triple double quotes. So you'll see the triple quotes here, and then the open chasm is here. And then it's basically, if we do this right, we'll see it's going to create the opposite, not the opposite circuit, but the qubits aren't, they're going to be flipped from how I ran. So here we go. So this looks right. And I could trace it on my phone, and I think I did this right. So that's a victory right there. So the next one is teleportation. So we're going to go ahead and save Chasm here. And then, so that image, or the way that I put the code in, is basically outputting itself in the opposite manner, which is good. Now, here's the Chasm code here. Actually, I'm sorry. That's the tricky part, is it's gray over here. You have to make sure gray here and the correct tab's open. It's always tricky. So on this specific one, I'm going to show you some visualizations. So this is important for a lot of things. And basically, it ran the first part, second part. Here's the third part. And this is a teleportation algorithm. And I'm going to perform a bunch of different visualizations. So this is them building it up. It's a Qiskit tutorial on teleportation. And this one, so it's still building up. And let's see here. Okay. And this one is going to output. So this is pretty close to the big circuit. Let's see here. So this, okay, this is another one. Now, hopefully we'll start to see. Okay, so in this one, I chose this plot barriers equals false. So if you see this is a generalized teleportation algorithm, and you'll see the barriers here, and you'll see the barrier there, and 3. So when you remove the barriers, it really condenses the circuit, makes it look nice. I've come across papers that do that. And then when you're building them, sometimes you need them. So this one, both plotted barriers or false, so it removed them, and then it reversed the bits. And this is kind of what I was talking about with that circuit that I got from this Roche and QCware paper. So you can perform, you see, and then here's the comma, that separates the two operations. Now, here's another one, and this is getting into, this is the MPL of, so this is matplotlib. And then here's another one. So this is text. So when it says output equals text, now this one is a little slow, it's latex. So I'm running it, and you see that asterisk, but the output is actually really nice. I was thinking about doing this for more of them. So it's just, it is black and white, this specific one. But I've heard other benefits of using latex, as far as saving images, those types of things for that specific circuit. And okay, so here's the bulk of it. So this is basically, it says style equals background color, light green. Background is light green. And then this one is going to be light blue. You see, the only thing it changed was from light green to light blue. And they're, kind of unique. I wouldn't recommend publishing these in papers. And you'll see the light pink here. There is no light, or I'm sorry, this is pink. There is no light red. Pink is light red, I think, in this language. So there's another thing is you can change the line color of all of these. So for the quantum registers or the quantum bits, you'll see green lines. And then for the classical, you'll see the dots. And that's due to this line color, light green. And then similar, this is going to be light blue. So light blue qubit lines, and then light blue dots on the classical registers. And then here's pink. So you'll see the pink lines, and you'll see that pink dots kind of shows up pretty well. And then you'll see this specific one, show index true. So this is Boolean, and this is the index. So this is kind of how we're saying to the next layer, I'll take a space between these. So here's the 1, 2, 3, and so forth. And then this specific one is scale. So scale equals 0.5. So you can see this is 1, or its default is 1. This is 0.5. And then the next one's going to be 1.5. So you see it's bigger in that specific case. So the next is C-reg style. I tried Q-reg style. I don't think it's a thing, but it's the classical bits, these lines, you can change to dotted, and then you can also change to dash. So you see the dash lines, dash. The barriers aren't that's not what it's referring to. And then here you'll see none. So you'll see no classical register lines there. It's kind of thing, it's like you make, like you figure these things out, and then, what would look good on your next publication, or what would look good on, whatever you're trying to do. And then the last one is a dash dot there. And then so here's the credits. So this paper is this quantum computation and quantum information, Cambridge is where it's coming from. Here's the Qiskit. And again, Qiskit is running at a, 8 QPUs, 8 CPUs, and 32 gigs of RAM, or it should say 31. So that's, it's basically things are being upgraded on their end. So that's pretty good. And so we're going to switch over to PowerPoint, and then that specific one. So here, and let's see. Google. Okay, so this specific one, so this is an output from last week, and it's basically getting creative with these circuits. You can stumble upon things, but I try to stick to the literature as close as I can, as far as that being a basis, and then combining other ideas. These are, quantum algorithms I'll be designing for neuroradiology, like classification. And this is basically an outline. So I went over, a lot of this as far as the, I'll be going over the literature modifications to other circuits and, trying to get better results. This is what I showed you, and this will show up in the deck there. So they use this word generalized. So when you talk about quantum circuits and Bell states, W states, GHZ, it's not gigahertz. It's actually three people's last names abbreviated. So the first one in Bell states is you're looking for maximum entanglement. So there's non-maximal entanglement. And then the W and the GHZs are 3 qubits doing that. And there's other circuits you can kind of see the W, kind of how it looks like. Now, quantum phase estimation is quite common. Implements measurements for Hermitian operator. The QFT, I'm going to show you a quantum Fourier transform. And the quantum teleportation, I did some visualization on that. And basically in teleportation, it's utilizing 2 classical bits in an entangled qubit pair. The receiver will have the qubit state and the sender will not. So that's what they call as far as teleporting, so you're using both classical and quantum bits. Now, super dense coding is you're sending 2 classical bits to another party using just a single qubit. So it's a little bit different than what we hear for teleportation. Now, here's a bunch of the building blocks in literature. So this Battelle M21, quantum circuits generating 4 qubit, and here we go, maximally entangled states. So when you're designing circuits, you have to be aware of basically the physics behind it. And then the second one is kind of a brand new paper, practical overview of image classification with tensor network quantum circuits. Their first paper into it was very thorough, looked like an awesome paper, but they said they weren't quite sure if doing it this way. And basically it was lining up a quantum circuit and turning it into a tensor just by how it looked, but a little bit more complicated than that. And then this third one, implementing MRI, and this is AlexNet, quantum learning, and I've shared this paper before. And then this other one, quantum Fourier transform, is more of a tutorial on IBM Qiskit, kind of backed up by Cambridge. Now, this specific one, these are 4 different circuits on their specific in their specific paper. Now, the issue I came across with this is when they said just P and P dagger, I wasn't quite sure the turn on the on P and what P dagger, because it's not quite used as much. So some of these have been phased out, but 2021. So I went ahead and ran them. So these are the results there. And again, it requires additional analysis on the right-hand side to tell, okay, well, you can look on the you can look before you run what they're estimated to be, and that's 100% accurate. Compare that to that, but it still takes additional analysis with a lot of these. Now, the Xanadu BMW paper I'd mentioned before, this 4-qubit circuit, their circuit, they said they can do 16 by 16 images. Now, I think it's based on qubit count because 2 to the 4 is 16. So that would be the 16 by 16. And then if you had 6 qubits, or I'm sorry, 7, I think that's 64. So that'd be 64 by 64, instead of a 16 by 16 image. So everything is just, kind of creeping up with quantum, trying to get image size up. And these are experiments, but it looks like, some of them are kind of unique. This last one, I wasn't quite sure, with the RY to include that at these 1 and 3 positions there. That'd actually be 2 and 4. So I ran one with and one without, and even with that one too. But again, these results are collecting data and then, thinking about which building blocks would be good for, specific aspects of medical imaging. Now, this paper I've shared before, and this is basically going deeper. So I did authors and then a 1 repeat, 2 repeat, 3 repeat, 4 and 5. So the 5 times 6 is basically adding 30 additional, layers to the original authors. So it's just getting the runs in, and I'll have a ton of data, which is good, so I can see how things, behave. Now, the QFT, or quantum Fourier transform, this is the generalized form, and a similar kind of thing, adding 1, 2, 3, 4, and 5. And then the one that kind of sticks out is this 2, the most with the highest probability. But again, it requires additional analysis. So here we go. So this is kind of what I showed you. And you can get this code, this link, this 1 and 2, it's link 1. And I'll be updating the links, for the real deck. But it allows you to do all these different modifications, and this is kind of everything on 3 different screens. So here we go: matplotlib output, text output, latex. We've got reverse bits, so that's what I was dealing earlier on with. So instead of going Q0, 1, 2, some circuits have to be built a certain way. So it just depends, on the circuit and what's published and that kind of. Sometimes they give you very little information about the circuit as far as trying to reconstruct it and quote their references. And then here we go. So here's a bunch of the different, say for instance, this is the show index. So you got the 1, 2, 3s, C-reg styles, dotted dash, none, dash dot, and then a scale 0.5. So just think it's up to your imagination. Now, the key thing with these things, and you could, I watch, I don't know, like I watch like at least 4 or 5 of these YouTube videos, and they say they must be reversible. So when you do something, so say on a block sphere, say if it's a NOT gate or X gate, it does something and then it comes back. So gates are built from the unitary operator, must preserve norms and probability amplitudes. No cloning theory is satisfied. You can't copy quantum data. That's what that means. So some of these classical data, I think there's only one of them that actually translates into a quantum circuit where it doesn't, you're not copying data, those types of things. So if you're not copying data, obviously you're going to need classical computers. I just actually heard, and for GPUs too, they'll be doing quantum error correction, these other hard parts that quantum can't do on its own and classical has a hard time doing. So figure CPU, GPU, QPU kind of stuff. Now the goals moving forward: robustness. This is MIT. Utilizes periodicity where appropriate. And again, some of these results seem to be tending towards, there's value in doing periodic networks, and I see those in the literature. And also keep in mind the neural networks, these days are co-designed, and then utilizing aspects of a conventional neural net or a convolutional neural net. And then this is the data set that I showed you that I got up and running. So now it's just a matter of getting it to train and then to test. And then if you've seen these before, I don't know if this is from Tom's Hardware. I didn't. This is from an INQ investor relations pitch. And this basically says number of qubits. So here you go, circuit width. So for that thing, you'll see 25 algorithmic qubits is what they call these. And you'll see things start to tail off, they can't go past 25, but number 2 qubit gates, so they didn't go past, say, like that's 500 cubic. I don't know how many I did on this specific circuit or in those other layers, but most of the experiments I ran are consistently 6 to 7 seconds. They're quantum class. It says both quantum classical, but it's a quantum computer with getting help classically. But I haven't run anything, I think, that was over 10 seconds runtime, on that specific quantum circuit. And then here you go. So this is the big news from this week: Cleveland Clinic and IBM, the first quantum computer dedicated to healthcare research. And I think this is in Cleveland, Ohio here, but you could see it being constructed. It's quite cool. It's not a huge quantum computer. I'm not quite sure. We could talk about the specs a little later. And this is basically the competitive advantage is in medical. There's been tons of studies, up to, I would say, 5 or 6 different papers looked at per week. So it's just culminating from September, all things quantum, and then many things, I would say, with the neuroimaging, neuroradiology, those types of things, just looking at things. And I want to end this presentation here. So there's been a number of people, kind of having a huge impact. So these are all successful single founders. They didn't have co-founders. So Jeff Bezos, 2018 pharmacy acquisition, Amazon Care. And then I think he stepped down from CEO in 21. So here you see the AWS for health. And then, in 23, clinical systems, AI, ML, and these are big things: analytics, medical research, a briquette. This is a service that you can hop on and do, run quantum experiments on, I think at least 4 or 5 different types of hardware. Michael Dell, so 2013, the Michael Susan Foundation, 2014, the Dell Medical School, 2017, Dell Seton Medical Center. So anytime you see that the Dell name there, or, Michael Susan. So health, wellness, they say over 2 million children affected, 31 active projects, over $100 million in active commitments. And then Henry Ford. So actually a little bit later in life there, he passed away at 1947, but 1915, the first hospital opened. Now, a lot of this was war related. So they actually lent this building to the Army and they used it as a hospital, so figure it was maybe not like fully up and running. 1947, the year that he passed, Etzel Ford Institute for Medical Researchers. So you'll see here, so basically today, and this is big in Detroit, I know, maintains 30 medical centers, 3 million plus outpatient visitors per year. So these are people that I would say, maybe started off doing other things. And then, it's a good thing to get into medical research is the clue right there. So I'm going to open up. Okay, so chat, rename. Okay, so you should be able to come on. And then if you missed part of this, basically there was a couple demos, inserting brain image data sets into a convolutional neural net, and basically, still troubleshooting with it's the training aspect. So if you have machine learning, you train, and then also doing a circuit in Qiskit, and then transposing it, and then doing teleportation algorithm kind of modifications to the visualization of those. So you should be able to come on, and I look forward to hearing, either, and definitely you see that shift definitely, for medical and, perhaps even different types of medical data sets, coming up. But that'll be the advantage is, with this coding and hopefully bringing on some other people to code that, they love coding in quantum, can do it hybrid coding, Python, Jupyter notebooks, Qiskit, the whole kind of thing. So yeah, any questions? We have a number of people returning here. So Carlos or Ron or Anisha?
Hey, Kevin.
Yeah, go ahead, Ron.
So the first thing you showed was some Python code for some image processing. Was that stuff that you were running in your own local Jupyter notebook system?
Yeah. So I downloaded the Kaggle data set, and you have to put the right JSON file in. And it's kind of convenient because the folders are actually under your C user username, like, and they show up directly how it does in your JupyterLab in your Chrome browser, whatever browser you're using.
Okay, I'm gonna reserve my comment for under the C. Um, and that was code that you collected from someplace?
Yeah, so they're based off a couple of tutorials. So they did three parts. The first part was an MNIST data set, and then the second part they just switched to local data sets. So that's kind of like a jump. So just and you can do more. Well, I don't know if you can do more with it, but obviously he did cats and dogs, which is kind of familiar. And I think that one's like 20,000. And mine, say for instance, it is like 5,700. But that's the whole goal, is basically to manipulate your own data sets.
Cool. You had made a comment about the chasm being the language of semicolons.
Yeah.
So from a compiler guy, the definition of a semicolon is a statement delimiter. And it's something that goes all the way back to the first version of C, and probably before that. And it's part of the C lexicon, and it's been propagated through many other languages, JavaScript, Java, and now we see Chasm and ESC and a number of other languages. So it's not the language of semicolons, it's just the standard way to terminate a statement. The other comment I would have is when you were showing the circuits and you were inserting the barriers, I believe they have more purpose than just making your circuit look pretty.
Yeah.
They actually adjust the timeline so that things happen at the right point in time as the circuit runs.
Yeah, I think it's multi, and like I said, I've had these slide around on me, and I've run circuits, and just knowing it wasn't right, but I didn't know how to fix it. But yeah, I think it definitely does that. It's functional.
Yeah, it creates a time reference point in your quantum progression. So that way you make sure, because if you don't put that in and you put those measurements on there, they'll happen whenever they happen. The barrier will cause them to wait for everything to catch up to the barrier.
Yeah.
From what I can tell.
Yeah, and before, I didn't know this, but if you just hit B and then tab, it'll do barrier Q for you. But then there, hit enter, and then you just click somewhere else in code. And before I was doing barrier, and then I was doing Q0, Q1, Q2, and there's basically, if you just do Q, it does all Q bits. I think that's what it does, or at least that's what it's been doing.
Yeah. All right, very good. So I saw you had 63 people signed up for this on LinkedIn, and actually I had seen that one of my contacts from IonQ, the lady involved with the bracket had signed up. Sad to see she didn't make it, but that could have been some interesting conversation.
Yeah. Yeah, I'm checking it right now, and the one I just did 25 minutes ago, it says 74 in Q, and then I've had it when it says something like 300, it might say 2 months to finish. So that circuit I was drawing, and then 74 might be a couple hours at the quickest. So I don't think that's going to show as far as results.
Yeah, you can play around with selecting the back end, try to find the machines that are less busy at a given time of the day.
Yeah, there's actually a code that says something, and then you type in least busy,
Ah,
I think
okay, yeah.
that's the command, least underscore busy or least something, you know,
Oh,
and
that's
it'll actually,
more.
it'll pick the quantum computer that, it's, you know, that's doesn't have a queue.
Yeah, that would be the right way to do it, huh?
Yeah. But I,
I think they finally got around to doing that. That's just basic load balancing. Perfect.
yeah, I haven't tried. Yeah. One of my, I did get an error that didn't map up with the 7 qubit, and then it created the circuit. So, or it created the results, the histogram. So I was kind of confused by that because at first it says, kind of switch over to a different um, quantum computer, and it
Yeah.
didn't let me select anything else. It was just basically asking me to select other different quantum computers that I wanted to. So
Well, originally in the free tier, there was only 5-bit quantum computers. I wonder if they're still running some of those, and maybe you're just when you submit a 7-bit program and it somehow finds its way to a 5-bit machine,
yeah,
that's where you get the
well,
error.
there is advantage in running a single instrument. So all of my data is based off that. So it's just like I could see that it looks like it improved in fidelity. Say, well, the one that made the biggest jump, it seems around this the 8 gigs of RAM, and then, or I'm sorry, 8 CPUs and the 32 gigs of RAM. When I saw that and I reran a circuit on the same quantum computer, my single probability for that specific run seemed to be a lot better. So, you can run things over the time. I remember in the university we'd have NMRs, and it was just a single one, and it was just, if it wasn't running well, you know, everybody ran off that. That was the only, like a 400 megahertz, which is actually bigger than I think a 3 Tesla MRI. But anyway, so it's interesting because, when I go on these other Python channels, and I just said, just start running, make sure you're running on whatever you can, because you learn a lot from that. And then you have to test it against literature, and then, read up on theory, especially for quantum, to see why you're getting why your histogram looks like that.